Okay, see, we are going to continue our talk on the dynamic equations of motion. Actually, last lecture we ended up getting this Newton equation in this way. I will add those extra terms later on. See, this was of course the equation if I had the origin at center of gravity, but if my origin what located at some other distance, and typically if I thought rg to be xg 0 0, because normally you would always choose body coordinate at a distance with xg. Normally the center of gravity is on the center line and origin also you will put on the center line, just x will be different. So, if I just took non-zero x, then the extra terms that comes out are that is why I left it free, you see. Etc. So, this is what was my Newton's equation of motion. That is what it says, that is all. Essentially this is what it says, but now as I was mentioning, today is going to be a rather important from the maneuvering point of view. See, now I need to figure out a way to represent the fluid forces, that is this forces. Okay. X, y, n are the fluid forces coming on the hull, remember, and all the forces, external forces to which it is excited. Now, this force x, y and n so this I can divide in terms of, let me call this to be generically as x bar, just to show vectorially. This will consist of, I can break it in components, you know, one will be what we can call hull forces, one will be because of rudder. So, one will be because of propulsion, and there can be other environmental forces. I will just explain what all this. See, there is this trajectory, the ship is going this way, velocity vector this, it has u here, it has v here, etc. Now, there is a rudder here. There is a certain amount of force coming on the hull. Why? Because remember that this hull is going in this direction, whereas it is oriented here. So, the flow comes like that, flow is coming like that to it. So, it is not really collinear, like it is not center line. So, that will give you some force on the hull and moment. So, I call this to be the hull forces. Okay. Now, of course, here in this I am trying to figure out all force components that is arising here. Remember, this is a situation where the body is undergoing a motion, it has certain u, certain v, maybe certain psi dot, Okay. So, all this thing, if I look at that are my inertia forces this side, that should balance with my total force acting on the hull. What are the total forces? I have first of all a forces arising on the hull because the water is flowing this way. See, as an example, suppose the ship was going on a straight line. What would happen? The net force that come is I am calling resistance force. Remember, that is what we call resistance, isn't it? Fluid forces acting on the hull in along x direction because the ship is going along x direction was resistance force. It is a fluid force. So, here it is not going along x direction, but with some kind of angle. So, there will be some forces created. I am calling it hull forces. Now, obviously, you have got this orientation because you have actually caused rudder to some angle, which has given some force on that. In fact, that is what has started the hull ship to turn. So, that is rudder forces. Now, propulsion force, because I have a propeller here, the propeller is going to give me a thrust. So, that gives me propulsion forces. And if I have, for example, waves, currents, wind, etc., I can call them environmental forces. Now, what we are going to consider only the hull forces. Why? Because consider this case. I want to investigate first, before the control surface, that straight line stability. Remember, where my hull was going on a straight line and I just caused it to turn by a small angle, disturb the hull. No environment because calm water. Just like resistance, I presume the study is in calm water, point 1. So, this I remove it. Propulsion and resistance cancels out because when it goes on a steady state at a given speed, exactly propulsion minus resistance will become 0. That is why it is going on a forward speed. So, I will not have any propulsion force here for my this consideration. Okay. I only want to know this side. Rudder I do not have because I am not applying rudder. Let us say, actually we are trying to find out firstly hull forces, we will model them eventually, but rudder also when I want to study just a bare hull with rudder fixed, not applied, rudder is kept fixed, I do not, it becomes a part of the hull, I do not operate it. Then what happens to the hull and its characteristic? What are the forces getting created? That is what I am trying to find out. Remember, that is most important because hull forces are created because of the flow around the hull. It was not there. Rudder force I am actually imposing, I am basically giving a rudder angle so that there is a force coming. Propulsion I am having an engine operating. Environment I do not have a choice, it was there, waves, current, etc. It is the hull forces that got created because I am turning or I am having a non-zero V, R, etc. Means it is not going along a straight line. That is what I want to look at first. So, we will be now trying to figure out how we can express, estimate, find out, determine the hull forces and then write the equation of motion. That is the most important part. Now, this part is the most important part. Now, you see here we will write this way x, y, n. Now, number 1, remember these forces are arising. Why they are arising? Because of the fact that it is having some v and some r and some u. For example, supposing and of course, the acceleration. Obviously, the forces must be function of u, v, u dot, let me write it down, velocities and accelerations, basically function of that is obvious, right, because for example, if I have a forward velocity, then only I am having some kind of a x force, that is resistance force, right. So, if I have for example v, what is v? An angle of attack. Remember that if the ship is going along this side with this u, then obviously I am having a small v, because remember this is my vector. right. See, non-zero V means what? Having an angle of attack, because only when it is going this way, u is along x axis, v will be along this axis, and this is the vector. So obviously non-zero V means it is going with an angle of attack, and now of course it may be having an acceleration on this side, sway. So what it means is that these forces will be necessarily a function of all the velocities and all the accelerations. They are functions of, they will depend in some sense. Okay, that is the most important point first we understand. So this has to be understood, that these forces, maneuvering forces and motions and moments will be function of all possible velocities in a general sense, linear velocities, rotational velocity and accelerations. Now this we keep in mind, and now we will see how we can have a so called Taylor expansion type thing. Now what is happening? Now keeping it aside, let us now look at this, a function. See here, by Taylor expansion I can always expand, you know that if there is a graph function of x against x, and if I knew its value at some position x0, that is fx0 I knew, then f at x becomes fx0 plus x, sorry, this is a Taylor expansion, everybody knows that. Right. Or if I call this to be delta x, then it becomes or rather let me call it fx here rather. You know that, right? This is the standard Taylor expansion. What it means is that supposing I have a function f of x, I know the value of the function at a neighboring point at x equal to x0, then I can express the function at x by expanding in a polynomial form the function about the neighborhood x0. That means I can say that this value is this value plus, you know, actually if you see the first term, that is nothing but the slope of this term, etc., etc. This I think is very standard, everybody knows it, and we need not elaborate that. This is in if you are going to do that in one dimension. Now supposing it was in a two dimension, supposing the function was function of x and y, then of course it will become function of x0 y0 plus delta x0, you know, fx, I will just write plus delta y0 fy plus delta, well, delta x0, just y, we call it delta y only, delta x square by 2 fxx plus delta y square by 2 fyy plus delta x delta y fxy, etc., etc. You know, similar way that we all know that. So this is a standard Taylor. Why I am saying that? Now you see the forces. What we go back to this equation relation. We know x, y, and n depends on this. Now what we want to know, remember now here, this is very interesting. This concept is important and interesting from all point of view. Initially, the ship is always going along a straight line. Okay. So, I have an initial condition where my u equal to u1, let us say, and everything else was 0. I will come back to that. So, I know my initial state of a ship moving on a steady straight line. It has got certain amount of force on that, which also I know, because that force is nothing but a resistance force. Now, what I have done is that I have slightly tilted it, given disturbance to it. I have slightly made a V and R and V dot and R dot and all that stuff. Then my purpose would be to find out what is the additional force coming because of that. So, this is I will try to explain this. See, my initial then in this case what happened, that means V equal to, well, u dot equal to V dot equal to psi dot equal to psi double dot equal to 0. All of them are 0 initially. Also x may be resistance, well, actually x will not be even resistance, when x will be 0, the reason is because if you take propulsion, x becomes 0. If you take propulsion, because resistance minus propulsion is 0, but never mind that, let me write it propulsion. Y is 0, n is 0. That we agree, because obviously it cannot have any y force this side, it cannot have an n moment this side. So, when I am going initially, I am just going on a straight line. Now, what we have done, we have given a non-zero values of these parameters. Now, so therefore, I want to find out what has happened to my y and x and all that. So, what would happen? We'll start with basically with y, because x is less important. We'll just try to show in y, then we will understand. Let me call this y. So, y is the y force. Let me just take that, is a function of, again if I write u dot v dot psi dot psi double dot. Okay. So, now y, see here, at u never mind, all this parameter is equal to y at initial value. Initial value is what? u1, because initially it is going at u equal to u1, but ui, you may call it ui, and everything else is 0 0 0. Okay. Plus, remember this is my, let me just write it down, u minus u1 dy by du plus v minus v1, or v1 means 0 here actually, v minus, or rather let me other way out, let me say initial etc. Then my y at u v etc. equal to y at ui vi etc. plus u minus u1 dy by du plus v minus v1 dy by dv plus psi dot minus psi dot 1 dy by d psi. These are three velocities. Then I have got u dot minus u1 dot see here, if I took only up to linear order, if I were to take this function where is this function, up to only this much, that is only up to linear term. That means I am presuming that it is too small, and therefore I can estimate that by simply this plus distance into the slope. That is, I am expanding the function by only a linear term, or you can say up to a first order approximation, which means value here is value here plus this distance into the slope. Very simple, value here plus slope into the distance give you this. See, this part is f x into delta x. If you take a slope, I mean that is what is called linear approximation, which essentially telling you that this graph has been assumed to be a straight line between the two. That is what we are saying, you know. So, if you take only, obviously that is a first approximation. If you want to go to the next level, then I have to take this term, etc., etc. This everybody knows it. So, here what I have done is that, supposing I expand these forces only up to first order, then I end up getting this. But now comes the fun. You see, now what is happening? U1, V1, W1, as I told you, initial values of which we have just now mentioned here. This is initial value, this basically U1, and these are all initial values. All the initial values are 0. That is, initially the I values are all 0. That is one. What is my Y value at initial? Also 0, because remember this value is the value in this direction in initial state. That means when it is going on a straight line. What is the Y force? Obviously 0, because there was no Y force. So, I end up getting for this particular condition, that is, if I were to expand Y about an initial condition which is the straight line motion, steady motion of the shape, then I have this 0, right. I have all this 0, etc. So, what do I get? I get here Y, U, V, etc. equal to U minus U1 dy by du plus V dy by dV plus you get also this then psi dot dy by d psi dot plus, we will of course this also will now neglect later on. Let me write in the other page, no, we will just come, because here this V dot, let me, I will go back to the next page, the same thing. Okay. See, the first term is 0, this term is Y, because initially, now this is this initially, you see, I am having this shape going on a straight line with only U equal to U1 and everything else 0. Now, when the hull is going on a straight line, what is the force coming in this side? What is the moment coming in this side? 0. So, the initial condition of Y is 0. What we are doing here, you know, is if you look at that, this Y, I will, before I write that here, I will show this thing. Y, initially Y was 0. This point, that is at U equal to U1 and all others 0, all else 0. My Y is here, but now I am having some parameter here. So, Y actually goes like that. Initially 0, why? Because there was no Y there, right. So, what we now I want, this is my Y, this is my Y at U, V, W, etc. So, what is happening, therefore, I will write it big way, Y U V psi dot U dot V dot psi double dot. This has become equal to U minus U1 okay. This we agree. Okay, now there are more to it. Now we will see still some picture. What is du by dy? Essentially variation of y against u. How much y is changing? How much is the sway force, y force? See here, this is my y force. I want to find out if I change u, make changes here, u minus du by dy, dy by du. Dy by du is change of y with respect to u. What is the change? If I change this side, is there a change in the y force? No. So, it is because of symmetry. So, this goes to 0. Similarly, if I were to, but this does not go to 0 of course, because there obviously is, if I give a v here, there will be y here. So, this is not 0. If I give a rotation here, this psi dot is rotation, also is not 0, because if I rotate there will be this thing. But about this again, what is this? I accelerate here, what is my y force? 0. So, you see, I therefore end up getting an expression which is only this 4 terms. Okay. So, what I end up getting is essentially this 4 terms. That means, I will now write for what do I get? Y will not write this value, it becomes therefore v into dy by dv plus v dot into, if I write now v dot plus psi dot into dy by d psi dot plus psi double dot into dy by d psi double. And remember one thing, these values v dot, psi double dot are very small values. Why small values? Because remember, they are perturbation from its initial state. So, I have an initial value which was 0, then I just make it small value. So, these are actually very small values. These values are all small values. That is to be basically kind of remembered, right. So, I end up getting, see remember here this are necessarily very small values. Why small values? Remember that my initial value was 0 0 0 0 etc. Final values are v dot, psi double dot. They are all just small change about the mean value. In fact, u minus u1, if I try to take u minus u1 is also small value, because u was let us say 10 naught, u1 would be 10 plus minus something. So, what therefore happened, I will come back to this expression here. So, this I have got, let me write also here this part of x here. If I were to write x in a similar this thing notation, you will find out, you will end up getting here u dot dx by du dot plus u minus u1. I will leave it for you to work this out. Actually, we can keep all the term v, and but the x expression is not very important. So, actually the x expression all are kept here, because you really do not know what may be the extra thrust coming because of those this thing. But if I were to keep n for the same reason of n is going to be simply v dn by dv plus v dot dn by dv dot plus psi dot dn by d psi dot plus psi double dot dn by d psi double dot. Okay. See, now I will tell you what we are going to do. We are not going to look so much on the x equation. The reason is because x equation is my equation showing how it is having a force in this side. So, this force and is going to cause me motion on the x direction. So, what would happen, instead of making a constant speed, it might be perturbing on that. Say instead of 10 knot, it might go 10.2 knot, etc., which is of not much interest for us from the maneuvering point of view. In the maneuvering, our interest is always this and this, because we want to see from the straight line how it is turning. X only causes it to go to on a straight line. So, therefore, we will be looking at this and this more carefully, because y is trying to make it go this way and n is going to turn it. Okay. Now, coming to that, now I will again now before we finalize the equation of motion, I want to discuss this terms therefore in a minute, and then we will. So, you see, typically we write this way, y as once again I will tell y, and I write y v, that is actually dy by dv. Okay. Then we will write this as v dot y y v dot plus, let me put r here, r is psi dot velocity. Basically, this term, that is this, say see here, what is the term? Rate of change or slope of either a force or moment depending on whether A is y or n against a motion variable which is either a velocity or acceleration, linear rotation. So, you have got basically alpha, there are 4 alphas v, v dot, r, r dot, there are 2 e in this case y and n. So, they have got total of 8 such terms. These terms are called hydrodynamic derivatives of the hull, linear hydrodynamic derivatives. Linear because I have expressed the forces only assumed it to be a linearly varying function about the mean. That means, I presumed y n are straight line about this. Okay. And what happened here, I say this y force is y v into v. What is y v? It is a slope. Supposing I want to find out how does y varies against v. What did I do? I said, okay, y at v equal to 0 is 0, y at v equal to v is equal to v into dy by dv, right. That is a very straightforward thing. So, what is dy by dv? It is the rate of change of y against v. Now, how much it is we do not know, but this becomes a characteristic of the hull. That means, I am saying that okay, let me find out for my given hull by some means how much will be the y for per unit v, then I will calculate and keep it with me. So, that becomes just like our BMT, KMT etc., a property of the hull, hydrodynamic property of the hull. That becomes hydrodynamic derivative. So, this is called, these terms are called hydrodynamic derivatives. And we will be discussing this at length, because the study of maneuvering borders or the central idea that remains is for you to understand what is meant by hydrodynamic derivatives. I will come back to that in a greater length again, this part, because it is very important. But now let me go back to the equation of motion part now little bit. That is also an important part. See, my x was m. There is an interesting thing you will see now. Which is I wrote earlier, but you see there is a problem. I think that is what we wrote earlier, right. Obviously, now we have to just equate both sides. Where did we read? Yeah. This is what same thing we wrote, v psi dot. Okay. Now the problem, see, is very simple. Now of course forget the x also, we could expand this way. Now I have the y, this side y in terms of Hall forces is this expression. I want to ask you this question now. I have this from Newton equation, force is mass into acceleration, but now I find that force I can express in this way. So I can say this is this. Can I say that directly or under some qualification? Let me first write and then I will try to tell you. So I can say, therefore let me just write down these two cases, or the case number 1 also if you want. We will just write down these two cases. We will not bother about this first one as such. So I can say this v y v plus v dot y v dot, because this y is this, right. Remember psi double dot is r basically. So I am just writing in v n v, but there is a small r n r plus r dot n r. Now the question is, see, I wrote this, but I tell you it is not exactly consistent. Do you know why? Because this side when I wrote, I presumed my v dot r dot are small values. When I wrote this side, I did not have any such approximation. This side, that is, if I were to use another pen, this side don't have any approximation involved that my v u psi dot, not u, v psi dot v dot psi double dot are small. We did not say that. This applies this side for any value. See this side, this is what we need to go slowly, you know. Force equal to mass into acceleration is what this side is, right. This side is this part. So I have force equal to mass into acceleration. Once again I will write down this way, mass into acceleration equal to force. This I said, this first part, but now I am expressing the force by this side. This force is this side, but this expression is not unqualified. This expression is for small values of v dot r dot. So therefore I also have to modify this if I want to determine the equation for small value of v dot r dot. What changes happens to this if I have that assumption embedded? Do you understand that? I mean, I want to make it go slowly. This side, mass into acceleration equal to force, this part of force do not have any approximation on the values or smallness or largeness of v dot r dot. It can be any value. This is valid, but this side, that is stating that force is equal to this, is based on the approximation that v dot r dot are small values, because they have assumed only linear approximation of the forces. Therefore, to be consistent, if I want to make this equation that way, I should modify this side of equation presuming that the same approximation, same level of approximation. Why? Now you will understand in a second. Actually nothing happens to all of that, but it only happens to these two terms. Let us take these two terms, okay, u and psi dot. Now u is u initial plus delta u, right, because u initial was not small. Remember, u initial is not small, it was maybe 10 knots, 15 knots. So u is of course perturbation of u initial, that is u initial plus minus something. So it is u initial plus delta, and if I were to multiply that with psi dot, then this is psi dot. I am just giving an example. Now you see this term, okay, this term, what would happen is ui I psi dot plus delta u into psi dot. Now you see this is small, this is also small. So, this term is second order term. I said that to you people many times, no, that small into small is small square, that so called the two smalls basically. Actually, I remember this from my teacher in Canada days, so I am very fond of saying that, you know. He kept saying that, this Chinese teacher, that it makes it too small, so it makes it too small. You just, you know. So, as a result, what happens? You are ignoring it. So, therefore, why the point is that it is second order. So, therefore, this term becomes ui into psi dot. So, this term will become ui into psi dot, not u into psi dot, and similarly this term will become ui into psi dot, ui being the initial velocity or the steady velocity of the ship. So, the only changes that happens in this equation is that this I can make this equal to this, provided this u I take here is the initial u. Okay. So, what is happening, therefore, I end up getting the relation. Now, I will write it down in the next page by combining these two, that I end up getting a relation that is m into v dot plus this u here, I call it in capital U psi dot. Capital U is my initial u, the steady velocity, plus x g r dot, let me call it r dot, is equal to v y v v dot y v dot plus r y r plus r dot y r dot. Then we have to assemble this equation in some form. Just 1 second, we can later on assemble. Actually, without validating, let me also tell you this part, that the x part, anyhow we can x part becomes, you know, m u dot equal to x u dot plus u minus u I, or that is capital U into x u. What I mean, in the x equation, the other terms, variation of x against v etc., can be neglected, because same reason, x force, although I mentioned, but x force in x direction would not depend on the v and y motion so strongly, therefore, we can ignore that. So, we can simply say this in fact this becomes your surge equation in a steady state case, because this becomes my resistance essentially x u etc. etc. So, we can still write that way. The next one is the other equation is, where was that, here, I. Well, I z I am just deleting, because I z is implied, you know, whenever we talk of I about the z axis now. So, let me presume that, you know, just for making things simpler, whenever I mention I z, because it is only one axis there rotation wise, I r dot plus m x g v dot plus this is u, capital U, remember, r equal to v n v v dot n v dot plus r n r. No, but we can of course then obviously we can manipulate this equation to bring it in one side, two side, etc. etc. So, I will see that the equation turn out to be minus the first one x u minus capital U plus m minus, let me write it down, x u dot equal to 0. Here we are, see, we will write this way, first v, then v dot, then r dot terms. So, v comes from this side, so it becomes minus y v into v plus v dot means here 1 comes plus m comes here, m minus y v dot into v dot, okay. Then r is here, this minus, it becomes simply m into u1. Wait now, oh acha, this is actually r. So, this is actually r, psi dot is actually r, right. So, if I bring that r here, then it becomes m u r minus y r dot, right, or if I call it minus, then I into r minus this and this y r. Oh, actually here there, sorry, there is an m, yeah, m will come of course, y r dot minus m x g equal to 0. Then next one becomes minus n v v plus, oh sorry, this is minus v dot we want to do. So, this is these two terms, n v dot minus m x g v dot minus r n r minus m x g u into r plus I minus n r dot equal to 0. In fact, this becomes my the classical linear dynamic okay. So, this is my classical linear dynamic equation. Just one second. This is the surge equation we are not much concerned with, because we are looking at the ship turning. If it is going on a straight line, well, if it is making some acceleration, we do not care, it is going in the same direction. Maneuvering is essentially as it is turning, making arbitrary trajectory. So, it is basically these two. What you see very interesting, you will find there is a force in proportion to velocity, force in proportion to linear acceleration, rotational velocity, rotational oh sorry, there is an r dot missing here. Okay. Same thing here, v dot r dot. What is the validity of that? It is valid only for small values, because I have linearized the expression. Now, of course, we will have to find out the solution for this equation, which gives rise to my v dot r dot would tell me how under the influence of the forces the like ship behaves. Now, see, the interesting part is this, see, the concept comes like that. Let us take an example y v. What is y v? Y force arising because of v. That means I have given a v. That means I mean I will come to this at a much greater length. Say I have given it a v, then it creates a y force, maybe it creates a force like that. Now, the question is, now see here, like that you will see, just here the example. Look at this, our example with a hill motion. If I were to heal it by an external sources, moment what happened, a static force comes if the metacentric height is high. See, I end up getting, what do I end up getting? See, I end up getting a delta, or I like to write it this way, writing moment this way, okay, or I can call delta GV GM into theta. So, if theta is this side, my force on the other side, right. So, I say it is stabilizing force, bringing it back. Here what is happening? Just see the analogy, I will come to this in detail. I give a V here. If I give a V here, the force that got created, you would supposing the force is on this side, which is what it is, this force is trying to resist and bring it back, right. So, if I want to give a V here, once again the hull force that got created will try to bring it back, because the force is on the other side. So, the tendency of the force is to make V as small and small, like here tendency of the moment would be to make theta small, so that theta becomes 0, the moment becomes 0. you know, like as the ship turns, what will happen? Theta will become progressively 0, and therefore the moment will become also 0. So we call it stabilizing. Supposing the moment was opposite side, gm was negative, what would have happened? You give a 0.1 degree theta, immediately the moment will try to make the theta a little more. When it becomes little more, the moment is even farther, cause the theta to be even farther, so it will keep on increasing, right. So therefore you understand here that these hull forces, now this is only one. So what are the hull forces here? All these terms, this yv, nv, etc., these terms, this etc., these are the characteristic of the hull, okay, and these not by isolation. If I were to solve this equation, which is what we will be doing eventually, and see the characteristic, you know, the characteristic of this solution, then I would know that what happens to v dot r dot. Initially it was 0, now I have given a small non-zero value, I left my hand, left that effect. Do they come back to 0? Do they increase? What happens, or do they stay as it is? You see, this is the question, like just like my theta question. If I give an external healing moment, a wind, I have got a theta created, a healing angle created, I remove the external force, thus the force generated in the hull, the moment generated in the hull because of hydrostatic pressure, tries to make theta small, 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 and eventually 0, or tries to make theta big, big, and big. This is the question we have to answer, and this question obviously comes out from solution for this equation. And when I want to solve this equation, I ended up knowing these quantities also. So I will first discuss tomorrow, next class, but first I will mention those quantities, and then eventually go back to that. Now just understand these quantities once again. I will just want to see you and close that with your analogy. See this first term, m minus yv dot v dot. Just see this term, then I will end this today's class. Now you see in equation of motion, in sea keeping, what did you find? Mass plus added mass into acceleration, right. Here I am finding mass plus minus yv dot into acceleration. What is then yv dot? It is nothing but added mass with a minus sign, because you see, what is this yv dot v dot? If I accelerate the body in the direction v with a v dot, the amount of force it got created. So you know, this way I will again discuss that. You will understand that this part is nothing but minus of added mass. We are just writing them with a different equation. In that I said m plus added mass into acceleration. Here I am saying m plus minus yv dot into acceleration. Obviously minus yv dot is nothing but added mass. Now added mass is a property of the hull. For a given hull there is an added mass. What is added mass? Essentially rate of change of y force, or force in a direction, certain direction, for acceleration in some direction. Heave added mass, force in heave direction for unit acceleration in heave direction. Same thing here, but then added mass is a property of the hull, just like GMT, not GMT, I would say KMT, BMT, AWP, MCT, TPC, they are intrinsic property of the hull. So this is also property of the hull. So I will just end saying therefore that, see, in hydrostatic we had all the hydrostatic parameter hull property based on hydrostatic pressure. In then came resistance. You have got resistance coefficient as property, some kind of property as a function of, you know, CF, etc., function of velocity also, of course. Then comes sea keeping, added mass damping. Now comes maneuvering, where hydrodynamic derivatives. All these are geometric dependent, all these are essentially fluid pressure integration on the hull, just that the pressure is coming for different, you know, from different mechanism, but they are property of the hull. We will discuss, we will end it here, discuss this, and interestingly we will discuss what it takes for my ship. What should this property be so that my ship becomes stable? Okay. This is the question we will be answering in next few classes. With that I will end today.